Hello friends, Mr. Burrell here. We are on the last lesson for Unit 9. We've talked about solving all sorts of different expressions that have logarithms and exponentials in them. We've talked about all sorts of different expressions, equations with logs and exponentials and how to solve them, different methods, all the tools in our equation solving tool belt, and we've added these log and exponents into that tool belt. So now we're going to go into a little bit of application. Why? Why have we talked about this for 2 full units? Why have we talked about logarithms? Why have we talked about exponents? Where can we see real-world problems where it would be useful to know these things in order to solve them? Well, I'm so glad you asked, because we're going to be talking about it right now. So let me get in here. By the end of this video, by the end of this lesson, I hope that you're able to use logs and exponents to solve application problems, some real-world problems. I also want you to know what the number e is, when it's used, what the natural logarithm is. We'll get to that. I also want you to know when to use each of the compound interest formulas. We're going to look at some formulas that are used to calculate interest, and we'll see those in just a minute. So first of all, I'm not going to go over this for super long because we talked about this at the very beginning of this unit. I'm just going to bring it up again. So you might remember this number, Euler's number, denoted by E. Remember, we talked about how the number E is a really special, useful, irrational number, kind of like pi. Pi is equal to 3.1415926, etc., 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 etc. E is equal to 2.718281828459, etc., 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 etc. It's called Euler's number because this mathematician named Euler first discovered it and started to use it. But I introduced this before. We're going to talk about it more in this lesson today. But remember that the number E is used in lots of applications, including interest. Notice on our objectives for the day I talked about compound interest formulas. So we're going to be using this number today. But it's used in interest, in probability. If the number E is used as the base of a logarithmic equation, like this, instead of like log base 10 of x, or log base 2 of x. If it's written log base e of x, we write that instead as ln x. So ln is just the way of saying log base e. It's just the lazy mathematician's way of writing a log with a base of e. So we're going to use this more today. Will I get real mad if you use this instead of this? No. But as far as notation goes, most of the time we'll be using ln when we're talking about a log with a base of e. And again, e is that 2.718, etc., etc. number. We'll use that today, and we'll talk about in our calculator where you can use that. Okay, where do I see logarithm and exponential functions used in the real world? I've talked about this a little bit already. You see it in a lot of physics applications with radioactive decay, calculating half-lives, exponential growth like the spread of sickness, hashtag corona. So we see exponent and logarithm patterns and functions expressed in a lot of real-world things that happen like these. The one we're going to focus on the most in this lesson is compound interest. So how do you use logarithms and exponents to calculate interest on investments? Or like if you're putting money into a bank account or into a money market account or into a CD or into something like that. We're going to use exponents and logarithms to calculate how much money you might have after a certain amount of time. So these are the formulas that we're going to talk about today. These are the formulas that people in business and people in banking use to calculate interest. So first of all, there's 2 different formulas. We're going to focus on this upper one first. So this is a compound interest formula. Sorry. So this first one is used depending on how often interest is compounded. So when you go to the bank, sometimes they'll say, okay, here's your investment account. We compound interest monthly, or we compound interest bi-weekly, or we compound interest annually or quarterly or whatever. That's how often your interest is being compounded. How often during the year that they crunch their numbers and compute and add on a certain amount of interest to your account. So in this formula, this is what each of these letters represent. There's a bunch of different letters here. So A represents your end amount, how much you're going to have at the end of this certain investment period. P represents your original amount, or how much you're starting with. So how much you're originally investing. Maybe I take $1,000 down to the bank, that's what I'm going to start with. That would be your P value, your original amount. R is your interest rate, and that's written as a decimal. So say you go to the bank and they're like, okay, your savings account gets a measly 3% interest. Your interest rate would be 0.03, or 5% interest rate would be 0.05, or a 15% interest rate would be 0.15. R represents your interest rate. N represents how often your interest is compounded. How often your interest is compounded, and that's usually per year. So say your interest is compounded every month. Well, that's 12 times in a year. Maybe your interest is compounded every week. Well, that's 52 times in a year. Maybe your interest is compounded only once a year. That would be once a year. So that N number represents how often is your interest being compounded in a year's span. And then T is the time, usually in years. So how long are you going to leave that money to sit and grow? Maybe you're going to leave it for 5 years, maybe you're going to leave it for 40 years, but T represents the time in years. So if I come over here, these are my different possible N values. So like if my interest is being compounded weekly, that number is going to be 52, because there are 52 weeks in a year. If I'm compounding monthly, that number is going to be 12, because there are 12 months in a year. Quarterly, if you think of how many quarters are in a dollar, there's 4 quarters in a dollar. So there are 4 quarters in a year. Every 3 months, they're going to compound your interest. So if it says your interest is compounded quarterly, that's 4. Semi-annually, that's twice in a year. Annually, that's once in a year. So that's how, depending on how often your interest is compounded, those are the values that you'd put into this equation. So this is the equation. I'm going to give this to you. You can use this when you use it on the test. But this is the equation to calculate this, these different things. So say I put $1,000 into an account at a 5% interest rate, compounding monthly for 17 years. I would put all those numbers into this exponential equation. It's an exponential equation because I have these variables up here as the exponent. And I'd be able to find out how much money I would have after 17 years. So that's where we're going to be using these interest formulas. And I'll go over some examples of different types of problems, different things that we would see as far as solving these types of problems. So this formula down here is a continuous interest formula. Some businesses use this, some banks use this. Basically what this formula does is compute what your end amount would be if your interest was compounded continuously. So instead of just like once a month they're going to compound it, or once a week they're going to calculate your interest, once a year they're going to calculate their interest. This is the formula for if you are compounding your interest continuously. Just all the time you're constantly compounding your interest and calculating your interest on the interest you've already received over and over and over and over again. That's what this formula does. So all of this jazz, if we're compounding continuously, turns into e to the RT power, which is where that e comes from. E happens to be the irrational number that helps us to compute continuous compound interest, which I think is pretty darn cool. Okay, so here are our formulas. We're going to go about and do some sample problems here. Okay, so question number 1. Fred borrows an amount of $1,000 from a bank, and the bank charges an interest rate of 10%, compounded continuously. Calculate the balance after 6 years. So in this, he's not investing money, he's actually borrowing money at an interest rate of 10%, compounding continuously for 6 years. So how much is he going to owe after 6 years if he doesn't make any payments. So which formula are we going to need to use? Well, it said this is compounding continuously, so here's our continuous compounding equation. So we need to find A, P, R, and T. Those are the variables in here that we need to work with. So what is A? What is the end balance? Well, I don't know. That's what I'm needing to find. What is my principal or my original amount? Well, $1,000 is how much we're starting with here. What is R? What is my interest rate? My interest rate is 10%, or 0.10 if I write that as a decimal. And then finally, T, what is my time? I'm going to leave that there for 6 years. Notice I don't have an end value here because I'm not compounding a certain number of times in a year. I'm compounding continuously. So, A equals, and I'm just going to fill in each of these values with the numbers that they need to be. So my principal or my original amount is 1,000. And then I have E, that's a number I can type in my calculator, to the R, 0.10, times T, 6 power. And as we're getting to a problem like this, I would strongly recommend either on your phone or on a computer using Desmos. I would strongly recommend using Desmos or a graphing calculator if you have one. If you have a graphing calculator or just any really scientific calculator, I would recommend getting one of those options to solve these problems. Desmos, it's free, it's online, you've used it before. But that'll help you to compute these problems. Okay, so I'm going to type this in my calculator just like this. 1,000. And then if you look over, some of your calculators are different, but if you look over on your calculator right over here on this side, in the blue, so in the second menu, there is an E to the X option. So if I click that E to the X, it's right above the LN button, it'll pop up this. Can you see that? That 1000E, and then it'll pull up an exponent, and I'm going to type that exponent just like that. Parentheses, 0.10, close parentheses, open parentheses, 6, close parentheses, enter, and this is my answer, 1822.12. So $1,822 is how much Fred is going to owe after 6 years if he doesn't make any payments. That's a lot. It's like $800 in 6 years. I mean, that's not like crazy, but it's not great. So $1,800 after 6 years, that's what the balance is. So that's our first problem, using our continuously compounded interest formula. And remember, E is just 2.718. That's my E value there. Okay. And again, these are all in your guided notes if you want to reference them. Hazel borrows an amount of $500 from a bank, and the bank charges an interest rate of 8%, compounded monthly. So now we're going to be using a different formula. Calculate the balance after 15 years. Okay, so I'm going to be using this formula now because I need to take into account that this interest is compounded monthly. So let's identify all these values. So what is the end amount? What is my balance going to be? I don't know. That's what I'm trying to find. My principal, or the amount that I start with, is $500. My rate is 8%, or 0.08. My N, or how many times it's being compounded, is monthly. There are 12 months in a year, so N is 12. And T, the time, is 15 years. Okay. So I'm going to put all those values into my formula here to calculate what the balance of Hazel's loan would be after 15 years. So A equals 500 times, parentheses, 1 plus 0.08 divided by 12, all to the 12 times 15 power. N times T, 12 times 15. So there it is. Again, you can type this straight into your calculator. I'd make sure and put parentheses around this jazz too. I'm going to go ahead and do 500 parentheses 1 plus parentheses 0.08 close parentheses divided by parentheses 12 close parentheses to the power of 12 times 15. So in case you want to see what my calculator looks like, in case you're using that, 500 times 1 plus 0.08 divided by 12, all in parentheses, to the power of 12 times 15. What do I get there? What do I get there? That's going to be A equals $1,653.46. Holy cow! 15 years, you only borrowed $500, and now you owe $1,600. That's the danger of borrowing money, my friends. But that's how much after 15 years you would owe. Okay. So, not always in an equation like this, not always am I just going to want to find out what my end amount is. Maybe I want to know, okay, if I want $10,000 someday, how much money am I going to need to invest? Maybe that's a problem that you're concerned about. Or maybe you're saying, okay, what interest rate do I need to get in order to get this amount of money? Or how long do I need to leave my money in the account at this interest rate in order to get this amount of money? There's all sorts of different questions you can ask yourself, and we can use what we know about exponents and logarithms to solve those types of problems. So I'm going to do a couple problems from the homework. Right now I'm going to start with homework problem number 10. It says, how much money should you put in a savings account now that earns 3% a year compounded weekly if you want $80,000 in 15 years? So first of all, which formula am I using? This is compounding weekly, so I'm going to use my this formula. Not my continuous formula, but my compounding formula for interest, where I can tell it specifically how often it's being compounded in a year. So let's find my A, P, R, N, and T values. So, how much do I want to end up with? Well, I want to end up with $80,000. $80,000. Okay, how much do I need to start with? How much am I starting with? My principal. Well, I don't know. That's what I'm trying to find. What's my interest rate? My interest rate is 0.03. What's my N? My N is how many times in the year it's being compounded weekly, so that's 52. And my time is 15 years. So let's plug out all that in. So I have 80,000 equals P times 1 plus 0.03 over 52. Boom, boom. To the N, 52 times T, 15 power. So notice now I'm solving for P. So first, I'm going to calculate, I'm going to calculate this. When I type that in my calculator, I got, let me go back here. When I type that in my calculator, I get 80,000 equals P times, and I got 1.5681. And remember, when you type that in your calculator, make sure and be real generous with those parentheses. So I have 80,000 equals P times 1.5681. Well, now in order to solve for P is being multiplied by this. How do I undo that? I divide by 1.5681. Divide by 1.5681. And alas, when I do that, I get P equals $51,016.87. If you need to pause this and go along and double check your work with me as you're going, you can. But in order in 15 years from now to have $80,000, if I have just a 3% interest rate, I have to start by investing $51,000. So, good to know, if you want $80,000 in 15 years and your savings account gives you 3% a year, you need to put $50 grand in there right now. Okay, I want to do one other type of problem. So, this is number 12 on your homework if you have that out. So if you put $7,000 in a money market account that pays 4.3% interest a year, compounded continuously, how many years will it take the account to reach $10,000? So first of all, which formula am I going to use? My compounding continuously. My continuously compounding interest formula. So I need to find A, P, R, and T. What's my A? How much do I want eventually? I want $10,000. What's my P? How much am I starting with? Well, I'm starting with $7,000. What's my R? What's my interest rate? Well, that's 4.3% or 0.043. What's my time? How long is it going to take? Well, that's what I don't know. I don't know how long it's going to take. That's what I'm going to try to find. So let me set up this equation here. A, or 10,000, equals P, or 7,000, e to the power of R, 0.043, times t. Okay, well, I have e. Remember, e is just a number. I have e to the power of 0.043 times t, and that's being multiplied by 7,000. So I need to isolate that exponential expression. So in order to do so, I'm going to divide by 7,000 on both sides. 10,000 divided by 7,000 is 1.4286 equals e to the 0.043 times t power. Well, shoot, now I have a variable in an exponent. If only I had a tool in my mathematics tool belt where I could get that variable out of the exponent. Wait! I do have a tool. That's what I have logarithms for. I can use a logarithm to change the form of this expression, so this right here is all by itself. So I'm going to use log base e. I'm going to change this to a logarithm, and it's going to be, and I'm going to write this two different ways for a reason. This is going to be log base e of 1.4286 equals 0.043 times t. Or, remember earlier in this lesson I said mathematicians are lazy. Instead of log base e, I'm going to write ln. ln of 1.4286 is equal to 0.043 t. And ln is a button on your calculator there on that left-hand side, or in Desmos, if you type in ln, it will recognize it as log base e. Well, ln of 1.4286, that is, what is that? Let's type that in. ln of 1.4286 is 0.3567 equals 0.043 times t. Well, I'm solving for t. If t is being multiplied by 0.043, I have to divide by 0.043. And I end up getting t equals 0.3567 divided by 0.043. I get about 8.3 years. So it's going to take you, if you invest $7,000 at a 4.3% interest rate, compounding continuously, it's going to take you about almost 8.5 years to get that up to $10,000. So those are all the different types of problems that you might see on this homework assignment in association with compounding interest formulas. So I hope after this video you're able to do these things. I'm hoping you're able to use logs and exponents to solve application problems, specifically our interest problems, calculating how much money you can make in interest in different situations. I hope that you know what the number e is and how to use a natural logarithm. And I hope that you're able to use each of those compound interest formulas. Those interest formulas are given on your homework. You can use those on the test. I just want you to be able to know how to use them in context and what each of those parts mean. So I hope that was helpful. That video was a little bit longer. Thank you for bearing with me. Please don't hesitate to ask me if you have any questions. And I hope that you enjoyed that video as much as I did.